Okay, so moving on to the biogeochemical cycles. These are going to be extremely important for the course, weaving them throughout the entire course actually, and they're seen a lot on the AP exam. So you need to make yourself very familiar with this vocabulary and comfortable with understanding how each of these cycles interacts with each other. So we're going to start by looking at some review vocabulary like reservoirs, which are anything that hold nutrients like the atmosphere or soil, even the ocean. Sinks are locations that are going to accept more materials than they actually release it. So they actually hold this nutrients a lot longer and have a long residence time versus the source, which releases more materials as they're accepted in a short period of time. So sink would be something like groundwater in the water cycle. The ground is going to actually hold that water a lot longer before it's released through to the aquifer. Sometimes groundwater actually stays around for a long period of time. So the first cycle that we're going to actually look at is the water cycle. It's a good one because you should have learned it back in elementary school. Know the vocabulary for the water cycle like evaporation, transpiration, precipitation, groundwater, aquifers, water table. The human impact on the water cycle and how we actually are impacting it by damming water, creating aqueducts to pull water from one location to a location that might not have it. Actually still do that in California. Irrigation, we use a lot of our water for the process of agricultural irrigation. And we are also over pumping a lot of our groundwater, depleting the aquifers in some locations. And that's happening a lot more due to agricultural irrigation. So big things with the water cycle. Water is going to be moved all around, and that's powered by the sun, because without the sun we don't get the temperature change to cause the evaporation to then bring the water up to the clouds. Then it's rained down through precipitation, and then it infiltrates into the ground or it runs off into the lakes, rivers, and streams. It gets into the groundwater or into the ocean through that method, and then again is evaporated again. Transpiration is the process of evaporation from plants. The ocean is a huge reservoir on the surface. The groundwater is obviously the one below the surface. But if you think about it, anything in the ocean is salt water. But once it does get evaporated, the salt stays around in the ocean and the water is what is actually brought up to the sky. The next one is the carbon cycle. And the carbon cycle you learned in freshman biology, but again, that was a little bit ago. So sources and sinks for the carbon cycle are important to know. If you think about trees are a big location where we're going to store a lot of carbon. Know how long reservoirs hold carbon, and the equation for photosynthesis and respiration is important for this cycle as well. The largest reservoir for the carbon cycle is actually sedimentary rock, with the second largest being the ocean. A lot of people actually flip these and get them wrong, so make sure that you know the differences between those. The ocean is pretty important though to the carbon cycle because it does take in carbon by dissolving it, the CO2 from the atmosphere into the water. Dissolves it through the shells of animals as animals take in that carbon to make calcium carbonate for their shells. And a lot of photosynthesis is actually occurring with phytoplankton in these locations. So the role of plants is actually really important in the carbon cycle. Plants and decomposers. So the process of carbon storage and atmospheric carbon dioxide is pretty much brought on by plants and decomposers. Again, carbon up in the atmosphere, it comes down through the process of photosynthesis, and those plants then have carbon in them. You either eat the plants, right, or you eat another animal that eats plants. Everything is going to die, so at some point decomposers will break that organism's carbon down and re-enter it back into the soil. Once in the soil, it goes either as a fossil fuel, coal, oil, natural gas, in the sedimentary rocks, or we can actually suck it back up through the roots of plants and go through the process that way. Don't forget that you can also introduce carbon dioxide in the atmosphere through fossil fuel combustion, as well as respiration. When we breathe out carbon dioxide. So humans do alter this process though. We are doing more mining of fossil fuels. So we're burning a lot more fossil fuels. We cut down forests, which means there's less location for photosynthesis to pull carbon dioxide out of the atmosphere. So that gets re-released. And we are actually adding CO2 to the atmosphere, causing global warming. Okay. The nitrogen cycle was probably a little bit more difficult for most people when they were in freshman biology. So I'm going to try to simplify it as much as I can for you. It's the movement of nitrogen from source to sink. The image above here can actually explain some of this to you. Some important vocabulary with this cycle is nitrogen fixation. So when the atmospheric nitrogen is converted into ammonia that can be taken in by plants, this happens two ways. You can actually have a lightning strike, or you can have nitrogen fixing bacteria. So the nitrogen fixing bacteria live on these nodule roots of legumes, so your peas and soybeans and everything like that. And once the plant and the nitrogen is actually sucked up by the plants, it gets into the plant system. And that's pretty important because all organisms need nitrogen to help make their DNA. So when organisms die or waste is produced, we actually call that ammonification. So ammonia is created, which is actually toxic in high quantities to aquatic life. This dead stuff is decomposed by bacteria and changed from ammonia to nitrite. So you can see that here. So here's the dead stuff, here's the waste. Changed from ammonia to nitrite. And then that gets converted into nitrate. And nitrate is the useful component for plants. Remember, that's the nutrients. So the plants can take up the nitrate. Animals eat the plants. We eat the plants, or we eat the animals. We get our nitrogen that way. And denitrification, right here. This is the process in which the nitrates are released back to the atmosphere. There's also bacteria that play a large role in this process. So without bacteria, we wouldn't have anything decomposing the organic matter. We wouldn't have the special bacteria doing nitrogen fixation, and we wouldn't have bacteria doing denitrification. So again, bacteria play a huge role in the nitrogen cycle as well. Both nitrogen and carbon, as well as the next cycle, phosphorus, we can't live without, but we also can't get it unless it's first put into plants or animals. So photosynthesis and producers are super important again. This is a review again of some of those other processes. So as we take a look at this, denitrification, again, we talked about how that puts the nitrogen back up into the atmosphere. But humans actually alter this cycle. So the Haber-Bosch process is actually what was used to mass produce nitrogen, to make nitrogen bombs synthetically. We use it now to make synthetic fertilizer, which allows for that process to be done a lot cheaper. It's actually widely used and causing most of our nitrogen runoff because now people are buying fertilizer more cheaply, and more of it's being run off or putting too much on the land. Burning fossil fuels releases NO2, which creates more air pollution as well. So not all alterations are bad. Actually, we start to plant more legumes to introduce more nitrogen naturally back into our soil. We do this through crop rotation. So one year the farmer might plant corn, the next year he might plant soybeans to put that nitrogen back into the soil. Another pollution issue is the production of acid rain, which we'll talk about actually later on in the course. But if you don't know, again, if you're having a hard time with nitrification or ammonification, here's the breakdowns of all of those as well. The nitrogen is held shortly in its reservoirs. the atmosphere is actually the largest reservoir for nitrogen. Okay, on to the phosphorus cycle. Phosphorus cycle is one you've probably never learned about. It's taken in for us by the process of eating plants. It's the only way we can get the phosphorus. So animal waste or dead things are broken down through decomposition, and those produce phosphates that plants need to grow. So that's why we do add a lot of the organic matter back into our farmlands, as well as our, your backyard, to get that phosphorus to the plants that you might want to grow. Weathering of rocks adds phosphorus into the ground. So as the rocks get weathered and eroded, that goes back down into the ground. The largest reservoir of phosphorus is actually rocks. So weathering and erosion do add to the cycle. Humans mining of guano, which is basically manure, like bat manure and everything else like that, as well as mining of rocks, actually lead to more phosphorus being released. And these are how we make artificial fertilizers as well. They actually will mine the guano and the manure to make artificial fertilizer. Phosphorus cycles, the largest reservoir is actually rocks and sediment. There is no atmospheric component to this cycle, so nothing up in the atmosphere. The weathering of rock releases into the ecosystem, and that's actually a limiting factor because you're not always going to see rocks broken down very quickly and weathered and eroded. So phosphorus comes into the ecosystem in that manner, and then it's recycled basically by decomposers and waste. So that plays a huge role into it. You cannot synthetically man-make phosphorus. So we will mine from rock or harvest the seagull poop or bat poop, the guano. And then human waste actually can also be used to redistribute phosphorus as well. So, actually, I'll come back here. Humans can alter the phosphorus cycle by using detergents with phosphorus, which runs into rivers and streams. This can actually cause eutrophication. So, you're washing your car, you're washing your clothes, if that gets dumped right out into the waterway, that can actually lead to eutrophication in that water. Untreated sewage is high in phosphorus, and we treat that before we actually release it back into the water systems. But there are developing countries that still don't have really good sewage techniques. If we have a sewage leak, like after Hurricane Katrina, that can actually cause a lot of phosphorus spikes. Crop fertilizer is high in phosphorus, so if we overuse fertilizer, that can lead to eutrophication. So knowing how to manage and treat those processes is important. So if we take a look here, reducing fertilizer use is going to reduce issues. Planting and maintaining vegetation buffers around streams that trap nutrients before the runoff occurs. Using natural constructed wetlands, marshes will actually filter a lot of this stuff before it hits the waterway and causes eutrophication. Improving technologies in sewage will reduce the amount of nitrogen and phosphorus that gets put into water systems. And reducing fossil fuel combustion will help with pretty much every cycle. So we need water to survive. We need carbon to basically make a lot of, remember we're called carbon-based life forms. Nitrogen we need for our DNA, and phosphorus we need for our DNA. So it's all really important. We need to keep it going.